During the following portion of this presentation, we experience technical difficulties. The problem does get resolved, and the quality will improve shortly. Thank you for your patience.
Okay, so we'll start off. It's a horrible echo. I'm hoping it's just me that's hearing it. A very quick agenda before we go through, just because it's one of those things you've got to do. Okay, so we'll spend a few seconds talking about who we are, what we do. We'll go into what the talk's about, why it's important, or why we think it's important enough to have fiddled around with it a little bit. Go into some background with timing attacks as they relate to the web. And then we start looking at timing as it shows up in our talk. So as a channel, as its own vector. We'll look at the privacy implications with timing attacks, look at some acronyms, just because the world can always use new acronyms. And at the end we'll stop and take some questions and hopefully not have stuff thrown at us. Okay, so really quickly, SensePost, we're a small South African company. We've been around for a bit, so we were formed way back in 2000, in internet years, that's ages ago. We've written a few papers on diverse stuff, so from application testing, network testing, even some stuff on worms and horrible tales of doom and destruction. We've spoken at a few conferences. Some of you might have seen some of our talks at Black Hat, which is why we're surprised you came back. We've been at Black Hat for about 6 or 7 years. We've written a few books, shows you what the publishing world's come to. And we've just done a bit of training. So we've had a few classes. Some of you guys that have been on the classes, and we see you recognize the faces. For the both of us, that's me. That one's Marco. We probably spent most of our time on this picture, so there's not a lot else to the talk. We spent most of our time on Simpsonize Me and never came back. Marco and I are security researchers with SensePost. We spend most of our time fiddling, breaking stuff, doing client assessments, client engagements. That's about it. Like every man and his dog, we've also got a blog. So if you guys ever have time to kill, visit the blog. It's better than a poke in the eye. So really quickly, what is the talk about? Okay, the name should give it away. Largely it's about timing stuff. Okay, that's a little bit generic because a little bit when we had started we wanted to time a whole bunch of stuff. So you see that timing is playing a more and more important role in lots of the assessments that we do. But it's one of those things that as soon as you spot it, you start to spot it everywhere. And it's one of those things, in the end we scaled it down to just timing as it related to web application assessments. Why you should care? If you're a developer, for a long time developers have been told to prevent information leakage. Okay, and a fair amount of work has gone into making sure that you don't just give information away. Nowadays, most of the web frameworks will give you a generic error message handler, something that you get almost out of the box these days. Okay, what you'll find is you're still leaking information via timing attacks, and it probably defeats the whole purpose. Okay, if you're a pen tester, what's interesting is unless you're checking properly for timing attacks, you're sometimes missing entire attack vectors. Okay, once we started discovering timing, one of the things that surprised us was how often it actually reared its head. And it's probably interesting for you because it's probably happening on your assessments also. Okay, if you like new acronyms, then we're there for you also. So we've got XSRT, which is not truly ours, and to try to make it truly ours, we introduced the D in front of it. So instead of just cross-site request timing, we're going to ponder distributed cross-site request timing, and we'll explain what it is and why we think it's cool.
So I'm going to take over and introduce Echoes at this point. Before we get into the cool stuff that we've got for the presentation, I will give a little bit of a background just on timing attacks in general and focus that towards timing on the web. So if we look on side channel attacks, so we step all the way back, side channel attacks have got this illustrious history against computing systems in various ways. And two of the hardware-based side channel attacks that we generally hear about are power analysis and radiation emission analysis. And the attacks there basically are whereby the attacker is attempting to infer actions of a device under observation based on certain physical attributes and characteristics that the attacker can see. And one of those is the power that the device will consume. The second one is EM radiation. But those two attacks are specifically focused against hardware. And for what we do, which is application level testing, they're kind of not within our area of expertise. So the third one there is time analysis. Now, time analysis is effective against both hardware and software. And it's interesting for us because it's possible to perform time attacks over networks, right? So instead of having to physically sit in front of a machine or in front of your device, you can actually perform this over some kind of network on the other side of the world. And of course, timing analysis would be effective against both hardware and software. In our case, though, we're focusing specifically on the software. So if we look at time attacks against software over the years, the traditional domain of time attacks has been in cryptanalysis. So there's been a bunch of papers over the years dealing specifically with time attacks. In '96, Paul Copper had one of the first results against RSA. On a local machine, he found out that he could time RSA operations and thereby recover bits in an RSA key. He also had results there against Diffie Hellman. A little later, Brumley and Boner had results against RSA as well, but the significance of their paper was that they were able to recover keys across the network. So they weren't limited to sit in front of the device. So immediately, at this point, we're starting to see that the usefulness of timing becomes apparent. And in fact, what they were able to do was to derive keys in an OpenSSL install. So it wasn't some kind of theoretical attack. It was actually a real-world effective attack. A year later, Daniel Bernstein derived a full key for AES across the network. Okay, now, AES has a property whereby it uses lookup tables. And what Bernstein's observation was is that lookup tables will cause an algorithm to be non-constant time. And so what he did was he wrote a custom network client and server, and from that he could derive keys. And his observation there was that in order to make this generic in real world, all you would require are more samples. So the attack is not less effective. Just a couple of years ago, I'm sure most of you recall, Clive Percival had his fairly well publicized attack against hyper-threaded processes, whereby, again, now returning to a local machine, a spy process running in parallel to a process that was conducting RSA operations could derive bits in an RSA key. And the way that he did that was with cache line hits or cache misses on the album cache of the hyper-threaded processor. His methodology was to observe the misses in the cache. From that, to infer the operations that the other process was conducting, and from that, he could infer which bit the process was dealing with at that point. So as you can see, there's been a bunch of papers. Obviously, there's a lot more, but these are some of the significant results with timing attacks in recent years, and these focus specifically on cryptanalysis. If we move a little bit forward to timing and the web, you'll see that actually we're moving backwards. In 2000, Felton and Schneider had a paper where they discussed the implications of timing attacks on the web. So at that point, 2000, the web was becoming understood, and Felton, who's got a strong interest in privacy, decided that this would be a fruitful avenue to explore. And what they did was they focused on privacy, so they stepped away from cryptanalysis and they applied timing attacks to the web. And what they found was that the timing attacks were very successful. Dead, not dead. So they focused on privacy specifically. They had 4 attacks. 2 of those are of interest. The first one was based on JavaScript, we're using JavaScript to time requests to pages. They could determine if that page had been in the user's cache or not. So obviously, if the page is in the user's cache, the load time is very short. If the page was not in the user's cache, the load time would be a little bit longer. And the second result that they had was that they used a Java applet to initiate DNS lookups. And based on the timing of the DNS lookups, they could determine if certain queries were in the DNS cache. So that's a DNS cache snooping attack based on time. So as we can see, there has been some work in the area of timing attacks in the web, and we'll get to one more shortly. But the last point on the slide basically points to it's not actually related to timing, but we want to introduce it since we use this technology. In 2003, Lars Kinnaman he basically released this little Java applet, or this piece of JavaScript that could interface with Java in order to pull your local network interfaces into JavaScript. So basically what he showed was the interface between JavaScript and Java classes, and using those in a web page. So this is the final slide on timing. I called it Web 10.0. It's a pun. I thought it was pretty funny, but clearly it's not appreciated. Last year we had, at Black Hat, we had two separate JavaScript-based port scanners were released by both Grossman and Nitzilkowski and Spy Dynamics. And both of those used an implicit timing attack. It wasn't explicit. So what they would do is they would attempt to load a page from a particular host on a particular port using a variety of tags, script, image, or whatever. And they would then wait for a couple of events to happen. One of the events that could happen was an on error because the page failed to load. Okay? And at that point, what you're doing is you're using an implicit timing attack. You're waiting for a timeout to occur, and from the timeout, you're inferring a particular state. And in this case, the port's not actually closed. It's probably not there. It's probably there's not a host there if the connection times out. And then this year, in fact, Andrew Bortz and his colleagues from Stanford released a very interesting paper on timing and the web, and really brought explicit timing attacks into web applications today. And what they discussed were two separate types of timing attacks. The first was direct timing attacks. In a direct timing attack, what they would do is the attacker would make requests and time those requests and infer information. So for instance, the kinds of information that they were inferring were whether usernames were valid or not. And they were also inferring, for instance, the size of a user's private galleries or picture galleries in a photo gallery application. So those were direct timing attacks where the attacker would say, test this username. Based on the timing of that request, I can say if that username is valid or not. And the second item that they introduced was what they called cross-site timing. Now, Harun will no doubt expand on it a little later, but basically, when we were coming up with this presentation, we decided upon this term and then searched for it and found the Bortz paper. So it was a little disappointing for us, but also exciting to know that other people are also thinking about these same kinds of things. Madness in numbers, I guess. So their cross-site timing attack went as follows. Basically, they would load an image tag and point that at a particular website, and then they would also have an on-error handler for that. They would point an image tag, for instance, at an HTML URL, and because that HTML URL is not an image tag, it would generate an on-error, and based on that, they could determine whether sites or whether there was information to be had from the timing of the request.
Okay, so the first direct thing that we're going to discuss, so straight off our talk, is the importance or actually playing with timing as a communication channel itself. When you're doing any sort of app testing or any sort of pen testing, one of the first things that you're going to start looking around for is a solid channel between you and your target. If you're doing network testing, it's pretty obvious. If you plan to extend your influence on the application, it's a requirement. So we're going to take a look at the progression of command execution attacks, and some of it is pretty ancient and old school, but just where we think the stuff's relevant. Okay, so oftentimes in the past, we'd find that the application itself gave you some sort of channel. Okay, so when we're talking about channel, we're saying we want to execute something, we actually want to see our results, or we want to get our results off the system. And in the old cases, it was pretty obvious that you'd find, if this shows up half decently at all, okay, in really old cases, it was pretty easy. The application itself gave you a channel. Okay, so you won't find many of these anymore. But for something like this application executes a ping command. After that, we get to inject our own commands. Okay, and what you'll see down here is that the app itself starts giving us our data back. Okay, if you're doing app testing against something like this, you should probably give the customer their money back. But in something like this, it's pretty straightforward, and you've got your channel, it's all clean. Where you do find this still a lot these days, so you're not going to find many old school Perl scripts around that just allow you to add queries. But what you will find a fair bit, and I suspect my hyperlink's not going to work, what you will find quite a bit is cases where, if I can just pull it up. Okay. You will find cases where friendly SQL queries allow you to get too much information. Okay, so if we just log into this, I'm not sure how that actually shows up on screen. You'll often find instances with SQL injection where it turns out some data is being returned to the attacker, in which case all of you should be thinking you can use union statements, you can use more complex SQL queries to try to get more information back from that. Okay, so if we take this, you should be able to throw in something. Can you guys see my typing at all? Okay, can you see that I can't spell? Okay, name from sysobjects. Okay, so we should be able to throw in more complex SQL, and again, it's pretty straightforward. The application's going to give us a channel back, and we can start doing coolness. Okay, so this is slightly more common these days than a straight bird's eye style CGI, but you will find it in, that's my browser walking, but you will find it in a fair number of applications where SQL is being used to return something to the analyst/user. Okay, sometimes the firewalling on the system is so poor that the whole thing goes out of the window. So if any of you on any of our training courses, typically you'd use this application to send yourself back an Xterm or send yourself back a netcat. Okay, and in that case, you don't actually need to worry about a channel. The whole system is there for the rapage. Okay, so what we're going to start looking at now is when applications like that start getting a little bit tighter. Okay, and we came across this application or a version of this application a little while back where as part of the application they actually had a search portal. Okay, and the search portal pretty much used a snippet of code that looked something like this. Anyone want to take a quick guess at what that snippet of code is doing horribly wrong? Or what it's vulnerable to? Okay, if they don't sanitize your user input, they're actually vulnerable to injection through regular expressions. Okay, so because of regular expressions eval command, you're actually going to be able to inject a regular expression in there. Okay, so for example, if you threw in something like that, well, let's actually see the search working, just so I know that Marco's image does. Okay, you should be able to put in a search term. It should come back and decide actually that's in its database or not, based on its regular expression. Okay, but once you figure that they are injectable, you should be able to do something like that. submit your query. Now, uname possibly did execute or possibly didn't execute, but sadly, we have no way of knowing and no way of confirming that. Okay, on the site in question, actually, their network was set up so that we couldn't get any return packets from this application. Okay, because when you're faced with a situation like that, normally you start saying, let's connect back, let's ping back, let's telnet back so that we know that we're executing. Okay, in this case, we actually found that the application was fairly tight, or the server was relatively well hardened, sitting behind a relatively well configured network. So no packets were coming back to us, and actually it turned out we didn't have the ability to write to the file system either. Okay, what we did find though, I made this bigger so that you guys could see it. I suspect I might have overdone it a little. Okay, so what we're going to go with here is taking in just a sleep command. Okay, so if we take sleep into that search, instead of just running a uname, and we tell it to run a sleep instead, what you're not seeing, because it's clearly off the browser, is that this thing's now taking a few more seconds before actually returning to us. Okay, so what it's giving us here is clear confirmation that it is doing its sleep. Okay, you should see that it's sleeping for 10 seconds. And you start to see that timing starting to present itself as a reasonable channel. Okay, so if we go back and start to see how much we can fiddle with, we actually figure that within our regular expression, we can call another instance of Perl again. Okay, so instead of just telling it to sleep, within the regular expression, we're telling it to call Perl and tell Perl to call sleep. Okay, and the reason we're doing this is just because we want more control over the results of our sleep or over the results of our command. Okay, and you see that that ends up being successful. And essentially, this puts you in a position to start doing coolness. So instead of just telling it to sleep, the command under it actually says, run the command uname, then grab the first character of your output and grab the ordinal value of that character and then sleep that amount of time. Okay, and so we can string this along and then say grab the second character, sleep its ordinal, grab the third character, sleep its ordinal. Okay, and so what we ended up with at that point was a script called timing.py. We're not very creative when it comes to naming stuff. Okay, and so if we run a uname command like we did on that box, you should see that you get the ordinal for S, which is 83. It slept 83 seconds, comes back with S, sleeps 117 seconds, comes back with U. Eventually, just by timing the sleeps, we can pull out the full results of whatever command we inject. Can anyone see one of the big issues with that? Okay, absolutely. Our analysts kept falling asleep. So the result of that uname at the best of times would take about 8 minutes, okay, to get you Sonos. And what's worse than that is it had very little margin for error. Okay, so if we go back there, if it expected 83 seconds for an S, a little bit of jitter on the line could have taken you anywhere. Okay, and it's relatively easy when you're trying to get Sonos, because you can fill in the blanks, but if you're trying to download binary files, it's going to start to suck. Okay, and this was largely just because we were a little bit stupid about it, because with a little more thinking, you could say using the ordinal is really stupid. If we're already in Perl and we've already got our results, let's instead break the stuff up into a binary string, and then for binary we can sleep 0 or sleep 1 or some multiple of it to get what we want. Okay, which took us to our second version, which again was cunningly named another time. Okay, which aiming at the same thing. That looked wrong. Okay, which one time. Sorry, like I said, our names are not very inventive. Okay, so it took us to a script called one time, which basically said, give us the command you want to run, and then tell us an arbitrary time. And what the 2 seconds is, or the 2 second here says is, if you get a 1, sleep for 2 seconds. If you get a 0, sleep for 0 seconds, so that we can tell the difference between both of these bits. And so this is using the same search box that we just saw. This time it's running on our machine, so it's actually the results on a Linux box, but your results should be a lot more usable time-wise. In fact, like I said, we are a small security company from South Africa, and with our bandwidth, we barely notice the difference. This is about what our Office connects at anyway. Okay, so using this method, we're able to pull data off of CGI or some application that's giving us this sort of behavior. And I'll kill this now gracefully before it actually embarrasses me in front of everyone. Okay, no. So one of the good things about this is you've got a high margin for error. So if we decided there was latency on the line, we could tell it for every bit that's a 1, sleep 10 seconds and sleep 0 seconds. And anything between 0 and 9, it's going to decide is a 0. And anything 10 over, it's going to decide is a 1. So it's pretty reliable. That's its null bytes, which I was hoping to stop talking before. But, okay, so if we go back now to SQL injection attacks, or go to a classic SQL injection attack, and I'm going to bounce around a whole bit, what we find is, again, SQL injection attacks way early, so in 2001, gave us a channel in itself. Okay, so if you wanted to do stuff using a SQL injection attack, one of the things that you could relatively easily do was use the application itself as some way of getting what you wanted. Okay, so if you had an app that was vulnerable to pretty 101 SQL injection, you are in the position to say exec master xp command shell. Sorry, my exec master dot xp underscore command shell. Okay, and you were relatively easily able to say something like old school is cool. Greater than C inetpub, if you could spell, root /os.html. Okay, and if that went through with something like that, you're in the position to go there and directly surf your results. Okay, so again, it's pretty old-fashioned, and you're unlikely to find this in many places these days. Anyone know what the big thing that prevents this from happening on most real applications is? Okay, disabled stored procedure, which we'll get to. And also these days, you're unlikely on any serious application to find the web server and SQL server living on the same box. So you probably did write to inetpub root, but it's not on the box that you're actually facing right now. So you've created your old school page just somewhere else. Okay, so we started to need, as soon as the SQL server and the WW server split apart, we started to need some way to confirm that our commands were actually executing, or to confirm that we were doing something on the target box. In some instances, we found that those boxes could talk clean out, which was a pleasure, but that stopped happening around 2003 or so. Okay, so at that time, what we were going for was you exec your command, and in some way or the other, you get your command to talk back to you. Okay, so you try ping, you try SMB, you try netcat, you try just about anything. And about the same time, what people figured out was that it's relatively reasonable to start using some form of timing also. Okay, so instead of echoing old school is cool, what we could do is simply say ping yourself 20 times. Okay, and based on the amount of time that that page took to come back, we're in a position to say that we are executing our commands. Okay, now if you combine this with what we just saw with onetime.py, you can start to see where the stuff is going. Something else that was interesting was often you end up using DNS. Okay, so the first command that you execute on the box happens to be nslookup mu.mu.mu.sensepost.com, and then you sit and you watch your DNS log files to see if anyone requests mu.mu.mu.sensepost.com. Okay, and we generally like DNS because at some point DNS makes its way out of your network. Okay, and generally you'll find even on relatively well-hardened networks, even through a DNS chain, something comes all the way out, something makes a request for mu.mu.mu.sensepost.com, and we get to confirm that our stuff's actually executing.
So, for a while when we've been going through these DNS tunnels, specifically at SensePost, as an example of trying to determine if we've got command execution, there's a whole bunch of tricks that were sort of floating around the office. And I guess it's certainly not unique. What it normally boiled down to was your knowledge of the Windows shell. So what we found was that if you start with some fairly horrendous Windows shell scripting, you can try to initiate commands. So you can execute commands, and based on that, you can try to start deriving the results via DNS. So if I switch to, not there, I want this guy. So what I've got here, basically it's going to run off your screen, but there's a pile of,
Use the green button.
use the
Green button.
use the green button. Right. This Mac stuff is all new to me. If you've got an injection point that allows you to execute commands, what we can do is we can start to put in little snippets of shell scripting. And so this particular one under DOS or under Windows will execute the command over here, the R and the C drive, and for what it'll do is it'll break it up into tokens, right? So for each token in each line, it will take the first token and it'll initiate an NS lookup of that token appended with sensepost.com appended. So we can take this injection string, flip to the browser, and guess I didn't cut that. Okay. So what I've got here is I'm going to inject this into the browser, but in order to verify if the stuff is actually coming back, I need some place where we're going to monitor these requests. So typically what we would do here is, because we own sensepost.com domain, we also control the name server where those requests for sensepost.com are going to arrive. So what we'd do is log on to our DNS server, start up a TCP dump, and wait for these requests to come back. So what I've got at the back here is TCP dump that's going to be running. I'm going to execute a dir in the C drive, and what we'll hopefully see are each of the first tokens coming back. So submit that. And you can see it starts to take some time. And on this side, we'll see that there's blah.txt, there's boot.ini over here, and so on. And so we can get file names based on this fairly dirty shell script hack. But this method's got a lot of problems. And what we find is that it works for small pieces of data. So for file names, for instance, it's relatively okay. But the problems that we find are it sucks for anything binary. So because this is DNS, what we have to do is look up domains within a certain character set, otherwise NSLOOKUP is just going to barf. So we can only look up ASCII values, we can only look up alphanumeric characters with a couple of punctuation marks thrown in there. So we can't do binary over this. And it also breaks very nicely on spaces. So if there's a space in a file name, or if there's a space in command output, then we lose whatever's after the space because we're tokenizing on spaces. And there's ways around that as well, but in essence, they're all just hacks. And the final point, which is fairly significant, is that that method sucks for anything over 255 characters. So if your output, even if it's a file name, or even if it's output of a command that doesn't contain spaces, it's only alphanumeric, if it's over 255, NSLOOKUP's also going to barf, because DNS domain names just can't be that long. So what we developed was a little tool called Squeezer. Squeezer is a fairly generic tool. One of its channels that it uses is DNS. And so what we've done with Squeezer is added a DNS tunnel to it. It was inspired a little bit by Sequoia's Automagic SQL Injector, which I guess if you're doing web application assessments you've used in your time. And it was a very nice tool for what it did, and certainly at the time it was pushing the envelope. And we've taken that idea of sending commands or causing actions to be taken on a server and drawing them out separately into Squeezer, and we've just brought it a couple of years into the future. So what it gives you is a simple shell, like Automagic SQL Injector gave you. It gives you a shell to pull server-side data into tables. Now, when I say pull server-side data, that means anything that's sitting on the server. So that could be data on the file system, that could be command output, that could be data which is actually sitting within the database. And what it also gives you is a return channel to get that data from the SQL Server to me, who's the attacker. And those two things are not related at all. And what it also gives us is binary safe transport. So now we don't have to worry about characters that don't fall into the DNS allowed range because we do conversions there. The final point it allows us is a reliable transport mechanism. DNS, by its nature, it's UDP for the most part. It's not reliable, it's best effort, but Squeezer builds reliability on top of that. What do you require if you want to run Squeezer? Ruby. So you don't have to have Python installed. You can remove it if you want. You also need TCP dump. We basically use TCP dump to capture our requests. You need access to a DNS server, generally, dependent on how you're going to run it. And the final point is you need a fairly large SQL injection vulnerability on an application. So when I say large, basically the injection point has to take a string of roughly 600 bytes, dependent on the mode that you're going to use it in. So the basic operation with Squeezer, with the DNS channel, is as follows. We initiate an HTTP request which causes data to be put into a table. Now that could be a command execution, and that's what we'll show. And then we initiate a series of requests after that, which basically go through that table with the output. We break those, for each row in that table, we break it up into blocks. We convert those blocks into hex. We add a header to that thing. We add a domain to the end of that, and then we cause a DNS lookup to occur. Okay, so it's the process is, it's not that complex. But the interesting thing with that is it's all done in that long piece of T-SQL. Hence, you need an injection point of about 600 bytes. And then finally, once those DNS requests are initiated and they come back to our DNS server, we've got Squeezer, which is capturing that stuff, decoding and storing. And the reliability is simple. If at the end of this process they're missing blocks, we simply re-request them. Okay, the second slide on Squeezer's internals basically is a couple of things to consider. The first is that the way that we get data into tables is not related to the way that we get data out of tables. So we can mix and match modes. We can say putting data in will come from a SQL query, or we'll put data into the table from a command execution. And the way we're going to get it out is, that can also vary. So in this case, we're going to look at DNS. Just now, we'll also look at timing. And that's how this ties in quite nicely with the presentation. So by default, when we want to initiate those DNS requests in SQL Server, the standard method would be xbcmd shell plus NSLOOKUP. But as has already been pointed out, often you'll find that xbcmd shell is disabled or the user doesn't have rights to it because you're not connecting as a sysadmin. And the question then arises, can we initiate DNS requests in a SQL Server without using XBCMD shell and NSLOOKUP? And if I'm posing that rhetorical question, the answer is, of course. There's a stored proc called getFileDetails. It's also an extended stored proc. And that particular stored procedure will take a path name and try to get some file information from it. Now, that's interesting to us because it doesn't require a level of privilege at all. All you need are execute permissions in the database. It's available to the public. So that makes at least two different channels. If we look up DNS through NSLOOKUP, we can specify more data. getFileDetails as a stored proc has got a limitation of about 128 bytes. And the reason for that is because it uses UNC paths. So the first graphic there shows that actually it is available to everyone. And the graphic below that shows a typical getFileDetails request that we would make. So basically that's a block that's been hex encoded. At the front it's got a header, and we pass that UNC path into getFileDetails. And what that does is it then initiates DNS requests, which we capture with Squeezer. So what I'll do now is I'll give you a very brief demo of Squeezer in its DNS mode. This will give you an idea of the network setup that we've got. Basically, there's an attacker. He's connecting to a web server, which passes requests to a database server. We don't have outbound TCP, only inbound TCP. But what we do have are a chain of DNS servers, so the requests will get back to us. Okay, so with Squeezer, what we've got, first of all, is a very simple config file that basically specifies what the target is. The host of the target is that. We've got the query string, so that looks somewhat similar to SQL Injector. We specify the method that we're going to use in all of those HTTP underpinnings. But once we load it, we get a very simple shell that if you didn't see it, there was a little bit of animation there. We thought we'd bring this.
Spent most of our time on the ASCII animation.
Yeah. Figured that was pretty cool. All right, so what it gives you is the shell. Now, while I'm functioning with Squeezer, we've also got this TCP dump happening on the other side, so you'll be able to see the queries coming through. So I'll do a very simple directory listing in the C drive. What this is doing is it's creating it's created a table in the database with the output of that command, and it's now initiating requests for rows in that table. That request breaks up the rows into blocks, hex encodes them, and sends them back to us. So you'll see, for instance, there's a request with a header at the front, lots of hex, and .sensepost.com. Because it's .sensepost.com, that stuff will always come back to us sitting on the Sensepost DNS server. And basically there we get the output of our directory listing. Okay. To show you that other commands also work and that it's not simply hard-coded into the scripts, we'll also run an ipconfig on that particular machine. And you'll notice that in the TCP dump output, what we've got is for every request, there's first an inverse lookup on the DNS server that it's sending the requests to. So this method is not quick, right? For every single block that we want, and the blocks are typically, for this method, they're about 130 bytes. For every block, we first have to initiate a reverse on the DNS server. If that thing times out, that's 2 seconds. If our request times out, that's also roughly 2 seconds. So the process is slow, but you do eventually get all of your output. What I can also do is switch away from the XBCMD shell method and drop down to that getFileDetails method. But I will show you first. Actually, I shall do this. So what I've done now is I've switched from command execution mode into SQL extraction mode. So the shell offers you a couple of ways of inserting data into a table which you'll extract. The first is command execution, but we can also pull SQL server data out. So for instance, at this point, what I can do is there's a few pre or hardwired queries. What I can ask for are all the tables in the database. And again, while that thing comes through, we'll see the request will start. This particular stored proc, the get file details stored proc, is a little slower because it has to initiate 5 requests before any info, or before it eventually returns. And it's not returning. Let's just do this. Okay, so we see the requests are starting to come through. And actually they look fairly similar. We've got a bunch of hex that's coming back. You'll notice there that for every line that we're trying to retrieve, get file details has to initiate 5 attempts at looking up that particular domain. So that works. The final thing that I want to show you with the SQL extraction mode is that we can also use our own queries there. So we've got hardwired queries, but for instance, if I want to extract all the tables in the database, all the columns for a particular table, I can stick this puppy in there. And what we'll see is the structure or the format of that command is very simple. Basically, you give it a column name, a table name to draw the column from, and a where clause. So it's fairly primitive, but it is effective. On the left-hand side, you'll see that the column names from one of our tables are being pulled out through a query that we've submitted to the server. So things that you could do at this point, once you've mapped the schema of the database and you see there's a users table, you see the users table's got passwords, you can now say, give me all the passwords from that particular table, or where the username is equal to admin.
Okay, so at this point, some of you should be shouting, we thought this talk was about timing stuff. Okay, and why is Marco talking about all this DNS stuff instead?
I worked really hard on that tool. Come on.
And it's got ASCII art.
Yeah.
But what becomes interesting is SQL Server's built-in wait for delay statement. Okay, so for a long time, SQL injection tools have started using wait for delay. If you look at SQL Injector, PowerShell, SQL Ninja, a whole bunch of them out there. But all of them use wait for delay in a slightly primitive manner as a type of Boolean operator. So they use it for, does this table exist? If it exists, wait for delay 20. If it doesn't exist, wait for delay 0. So at best, it's giving you one piece of information. Considering the information we learned, or the stuff we learned from Squeezer, and the stuff that we learned previously from OneTime, it puts us it makes it really obvious that we can combine the two, run a command, encode it, drop it into a table. If the data is sitting there as binary, we can then decide to sleep 0, sleep 1, all of that stuff. Okay, which first takes you to another piece of proof of lameness, because the first thing that we did, and clearly some of our code is not as good as some of our other code, was to do this in Python, okay, and we ended up with something called, I think it was anothertime.py, okay, and this gave us the ability to put in a command, and again, what this is doing is what we described earlier, run your command on the server, drop the stuff into a table, then depending on the binary, sleep 1 or sleep 0 seconds. Okay, so this is exactly the concept that we were doing with DNS, except now we're sleeping. Of course, at the time that we did it, we were sleeping a fixed amount of time. So I was either sleeping 2 seconds for every one or 4 seconds for every one. And I think when we first wrote the script, we wrote it because one of our guys was on an assessment. And I seem to recall that he didn't sleep for 48 hours. actually because he was waiting for the results of this thing to come back. Okay, so that was slightly inefficient and slightly suboptimal. I'm going to leave that running. It'll come back in a few seconds. And instead, we can move on to Squeezer doing the exact same thing, but slightly cleverly.
So, to carry on with what H was saying, Squeezer, if you remember, it splits the way that data gets put into the tables and the way that it gets extracted. So combining that, what we can actually do is keeping that front-end stuff of insertion the same, we can swap out that DNS portion, that DNS tunnel, and actually just insert a timing channel. And so thereby gain the same functionality that we had with the DNS, except this time we can do it through timing. What happened there? Oh, yeah. So, as you can imagine, these things are not supremely quick, but what I'll do is I'll initiate a similar...
Saw the animation?
I can play it again if you want. So it's as easy as flipping your channel from time or from DNS to time. We're still in command mode for Squeezer, so I'm going to execute a hostname as well. And this one's a little different from Harun's. Gives you a status update.
So what you'll see here is we're getting back status updates, but what Squeezer does slightly differently is waits for all the results to come back before showing it to you.
And on the right-hand side, what I've basically shown you there as well is that TCP dump, just to show you that actually we don't have DNS queries in this particular channel. This is all timing-based.
Can you explain why your time takes longer?
You go for it.
No, go for it. So do your histogram.
Okay. So while this thing runs, basically the problem that probably some of you are thinking about is, again, there the line's coming back. The one problem that you'll find is that determining how long to wait for a 0 and for a 1 bit is a little arbitrary. So our initial attempts at that were to simply go, okay, well, we'll do it, or we'll make it 1 second difference, and if it's not effective, then we'll just up it manually. So what Squeezer does in its timing module is it introduces a little bit of a calibration effect. So to cover that, you don't actually know how reliable timing is. By its nature, you can't be 100% sure of your results. So you will always get errors in this approach. This is not foolproof. DNS you can build reliability on top of. With timing, unless you're making the same requests numerous times, you can't ever be reasonably sure. But what we can do is, with a little bit of statistics, we can try to circumvent that. Now, my statistics are dodgy at best, but they are sufficient, I think, for this. And what we basically do is we calibrate Squeezer before we start to actually use the timing channel. So the calibration works pretty simply. All we do is we send out a bunch of, or we collect samples. So we ask for, by default, 10 0 bits, 10 1 bits, and we time them. And we do some simple statistics. So we discard the outliers, basically define ranges through which we expect those bits to fall. The reason that we define ranges instead of a threshold, because typically you would say, if the time of a request is 1 second or more, we'll make it a 1 bit. If it's less than that, we make it a 0 bit. What happens if it's 70 seconds? If it's 70 seconds, you can't make any such statement, right? Because you don't know if that's complete failure on the line, there's routing problems, and so on. So we need to define ranges. The way that we've gone about it is, I think, fairly simple, and it works relatively well. We basically define these two landing pads, as I like to call them, one for 0 bit and one for a 1 bit. Okay, so to move through this somewhat quickly, basically we can draw histograms here. On the histogram, we've got 0 bits and 1 bits. We define the landing pads, and anything in between or outside of that gets discarded. The last thing about Squeezer that I'll just mention, it also supports the SQL Injector.pl's HTTP error message channel as well. So Squeezer's got 3 channels, DNS timing and HTTP error messages. So it's pretty much a drop-in replacement for that, and it gives you more functionality.
Cool. So Squeezer should be available on our research portal as soon as we get out of here and get reasonable internet access. You should be able to download it. You should be able to fiddle with it. Marco just killed his mic. Okay. So what we're going to go on to next is to start to look at timing with the web for slightly different things. Okay. So when you're doing application testing, one of the things that comes across pretty strongly is that information leakage is a pretty big problem. Okay. One of the reasons analysts like it is because it's almost something you can throw into your report by default, something that says you should be using generic error messages. Okay, but typically it actually is a useful recommendation. So up there you'll find one of the popular news aggregator sites, and you'll notice it differentiates and tells us you've got an invalid login or you've got an invalid username. Okay, so if you were trying to run a brute force attack, that's pretty useful just to know which way to aim yourself. But actually, we've been beating on that drum for a while. We've been telling people that they should be using generic error messages, so you don't see that as often anymore. Okay, you don't get that in a large number of apps. But what is interesting is that you start to notice that there are subtle timing differences often present on login pages. It's just that for the most part, we actually haven't been paying attention to it. It's particularly prevalent, I used a big word, you see it a lot when hardware tokens are involved. Okay, and generally that's because a round trip time has to be made when there's a valid user as opposed to one that isn't made when the user doesn't exist. Okay, so we've set up an example of actually what we're talking about, okay, with some bank or the other, and its login thing. And the question here is whether you spot the difference. So we'll try a login for Bob, and we'll try a login for Marco. Okay, did any of you see the difference there? Okay, in this case, the application's giving us a whole 1 millisecond difference if Marco actually does exist or if Bob doesn't. And actually, we stole this live from some customer assessment that we were on, where we actually noticed this happening. Okay, and so what that puts us in the position to do is to come up with another badly chosen acronym or badly chosen tool name. So I'm going to kill this quickly and instead go to Python yet another time.pl. Okay, and this time we give it a names list, okay, and basically it's just going to try seeing how long it takes, seeing when it comes back, and decides if the user exists or not. From now we enter the realm of really dodgy scripts that may or may not work the first time, so you guys are going to have to bear with us. Okay, and what you should see there is the script actually trying to verify whether it's line noise or whether Marco actually exists. And I should do something that catches that error a lot better. Okay, and what you'll see down here is really simple. So not using any of Marco's histogram cleverness, it's just sending the request, deciding how long it takes, and deciding if the user exists on the system or not. Okay, so one of the reasons why that's really scary is, for one thing, we found it on a really popular banking site when we were doing this assessment. The second thing is, we took a look at a whole bunch of popular application scanners, so without mentioning names, and we looked at a whole bunch of their websites, and although lots of them punt every test or every sort of test that they're doing, not one of them made any reference to ever checking for anything timing related. Okay, so while it would make a big deal if you were returning different error messages for invalid login, invalid password, they absolutely just wouldn't notice if you were taking a full 5 milliseconds for valid users or invalid users. We've since put it into our Suru tool, but in honesty, we only put it into Suru after we started noticing this stuff happening. Okay, so if you're pen testing, you probably want to speak to your AppScan vendors and see if they'll put the stuff in. So we start to go to timing and privacy on the web, or privacy. Okay, and you've got to come across the same origin policy. Okay, the same origin policy is pretty straightforward. It tries to make sure that scripts running from page A can't get data or can't get useful results from stuff that's happening in your browser on page B. Okay, so the question is, how did Jeremiah and them do their port scanning coolness? And Marco explained it to you. Basically, they said, run the script here, try to load something. If it didn't load, we can infer some information, and if it did, we can infer other information. So after port scanning, the guys soon went to history checking based on CSS. And like Marco said, Ed Felton, way back in 2000, started talking about privacy by timing loads. Okay, so graphically what Marco was talking about, the user browses my site, I drop down a Java applet to him. The Java applet decides that it took this long to fetch Scientology.org logo.gif and has some sort of threshold. It decides that Scientology.org logo.gif came down too quickly, so therefore the user actually had visited that site before. Okay, so when we started playing with this, we thought we invented a new acronym until we Googled for it, and it turned out we were wrong. Okay, and what we started to ponder was the whole question of cross-site timing. So whether we could use my script to time your requests for other pages and how useful that would be. Okay, so like we said, Andrew Bortz this year, he's in the crowd, so you can buy him something, buy him alcohol afterwards. Okay, he wrote a paper discussing cross-site timing and its implications. And the attack that you end up with is pretty straightforward. So if you take the example of LinkedIn, the example down here is actually Facebook. Okay, if we made a request for facebook.com friends.php, if the user actually was logged into Facebook, this page would be returned to him. And if he wasn't, this page would be returned to him. Okay, and there'd be a very obvious timing difference in how long those pages take to come back to you. So you could pretty easily decide whether or not a user is or isn't logged in to some other site completely. Okay, so really simply, like I said, user visits us, we load these two pages, we make our call. One of the problems with this, again, is South African bandwidth. Okay, so in South Africa, someone loading Facebook takes a matter of minutes, and up here, someone loading Facebook takes a matter of milliseconds. Okay, so if you're trying this timing attack, you can't base it on a static number. Okay, so what we went for, and what Ports went for, was the concept of a base page. So in the Facebook example, you load a page that logged in and logged out users can fetch. You fetch the page only available to people who are logged in, and you calculate how long it takes between them. Okay, it gives you latency-resistant methods that should work. The question that has to happen is, what happens about cached pages? In our example, we load the page twice, just to make sure that the caching is not screwing you over. Okay, so the example that we used up here was basically figuring out if a user is or isn't logged in to a mailbox. Okay, and we have an example that almost always works. Okay, and if we just take a really quick, this is actually one of the other hard parts, getting Squirrel Mail working. Okay, so if some user happens to be logged into his mailbox account and then innocently visits your page or visits some page where you've had the ability to insert script, okay, what you'll find, what we're doing graphically here is we've loaded up 3 frames. The frame in one loads up the base page. In the second one, loads up the page that's his inbox. and figures based on this amount of time that actually the user is logged into webmail. Okay, so we should be able to test this and sign out there. And if the user happened to visit this again, okay, you should find that it comes back and decides that actually the user isn't logged in. Okay, and at this point, somebody should be saying, wow, you can tell a user if he is or isn't logged in to a mailbox. Okay, that's supremely underwhelming. Okay, but obviously, just like we've got those 3 frames, in our example, actually what we're in a position to do is have it actually go back to an attacker completely. So in our instance, you'll find while the page is being visited, another request is being sent to the attacker that says this user is or this user isn't logged in at that point in time. Okay, so it's a pretty effective way of getting past, at least in a little bit, this part of the same origin policy. Okay, so let's quickly summarize. We know that some sites would tell you whether a user is or isn't valid based on timing. We know that most sites would betray a valid login from an invalid one based on some sort of timing. And we know that we can use your browser to time stuff while you happen to be surfing. We actually waited a lot for that. Okay? So it happily gives us cross-site request timing and then distributed cross-site request timing. Okay, so if we take it in stages, you'll remember that with timing.py, we could say, is a valid user on the system or not? Okay, we were then able to implement that in JavaScript. So if you remember the original Python script that ran, that decided that Marco was valid based on time, we've now got the ability to do this purely in Python and purely in JavaScript. And because we're doing it in JavaScript, we can do it on your box instead of on ours. Okay, you bump into a small problem with the granularity of the timer with JavaScript. So it's not going to give you a granular enough time source, which will be a problem if you're trying to time things. But fortunately, you'll remember that Marco spoke about extending Java applets, which the guys were using to get your local IP information. Okay, so it was being used for JavaScript port scanning. And we find that if you import from java.lang.system, you can pull in nanotime. Okay, and so what this means is instead of getting just 416, you're actually able to get a much bigger number, which looks more impressive, but actually essentially gives you a more granular time source. Okay, so if we then agree that the granularity problem doesn't exist anymore, you should see that we can easily go from timing.py to timing.js. Okay, and essentially what this should give you is the ability, and this thing almost always works, okay, it should give you the ability of having someone visit your page, and while they're visiting your page, you having them do the timing attack to mine for valid usernames on the bank site that happen to be betraying time. Okay, so let's see if my cut and paste actually works. Okay, so what you should see is a horrible time glitch. Let's try that again so that it at least looks better. Okay, so again, in this case, something that should be obvious before anyone asks me about it, we don't have to make any of those frames visible. Okay, so essentially what happened is someone visited our page, we sent them a bunch of usernames, they're now trying that bunch of usernames against the bank site, and the moment they found a valid user in Marco, they get back to us and say, Marco actually is a valid user on that site. It's really cool for us, other than because we got to play the hamster music, okay? Because it starts to introduce the possibility of distributing your brute force attacks just via JavaScript. So if you happen to find a popular page on Reddit, like the hamster was at some point, or you get slashdotted, a whole bunch of people visit your site, you start farming off to a whole bunch of people these usernames, and essentially all of these users start using the cross-site request timing, okay, and all of them keep going until one of them decides that actually there is a valid user, his name is Marco, and they send that result back to you. Okay, so on your side it's a little bit of JavaScript. It gets pushed down to everyone who visits you, and as soon as there's a valid user, you'll get informed and you can start doing whatever you want. Now obviously you don't have to do it just for valid username. You can start using it in the future for things like session IDs. Okay, for session IDs, the thing stopping us right now is the ability to inject into a header, but we're pretty sure that that'll be overcome. Okay, so really quickly with really squashed text on this slide. If you're a developer, you want to make sure that you're not throwing information away just through timing. You want to start looking into standard cross-site request forgery type protection because you'll find that it overlaps here strongly. If you're a network security admin, touching on early Squeezer stuff, you want to make sure you re-examine least privilege. You'll find that often your SQL servers don't actually need to talk DNS at all. You have to start asking yourself if you would spot timing attacks on your network and start to ponder or start to figure out ways to counteract that. If you're a pen tester or researcher, for researching currently, one of the things we're interested in is to see if we can inject headers through cross-site scripting or XSRF attacks, because that's going to take this to a whole different place. Grab a copy of Squeezer from our website, drop us feedback. For everything else, visit us on the blog, leave us comments, tell us you didn't like Marco's hat. For the rest of it, we should be around if you guys have any questions. Anything? Anything? Yep.
Have there been any real pushes just on hardware development to prevent this sort of stuff, at least locally on the machine? So in other words, instead of just giving processes the quickest response, there's going to be anything like that where stuff won't work, not that
Yeah. So the question is, has there been development like hardware-wise to prevent such attacks? Because the attacks have been well known in crypto for a while, it's been well thought out, and so for most of amount of knowledge on it, but like most things on the web, we remake those mistakes every time.
On that side?
Yeah, sorry.
So